10 degrees C. The open squares are that at 60 degrees C. The H over PD at 60 degrees C is lower than at 10 degrees C. On the other hand, it has been said that loading process change from exothermic to endothermic when H over PD value is higher than 0.85. However, when the temperature change was given after the cathode loading has reached 0.94 at 10 degrees C, the H over PD decreased and finally coincided with the value at 60 degrees C. Next, decline loading is shown. This figure shows temperature dependence of D over PD between 10 degrees C and 60 degrees C for palladium in 1 molar LiOD. The D over PD at 60 degrees C is lower than at 10 degrees C. When the temperature change was given after the cathode loading has reached 0.85 at 10 degrees C, the D over PD decreased and finally coincided with the value at 60 degrees C. Next, this figure shows dependence of loading ratio on current density at 10, 30, and 60 degrees C. The D over PD and H over PD decreases in the order 10, 30, 60 degrees centigrade. To summarize effect of temperature, D over PD decreases with increasing temperature. Then, this result is consistent with the PCT curves. Therefore, loading process doesn't change from exothermic to endothermic, even when H over PD or D over PD is higher than 0.85. Next, I will to talk about surface modification. Thiourea is chemisoft on the cathode surface and inhibits the hydrogen desorption process. So, we investigated effect of thiourea. This figure shows effect of thiourea on D over PD for palladium in 1 molar LiOD at 10 degrees C. The green circles are D over PD in 1 molar LiOD without thiourea. The open squares are that in 1 molar LiOD containing thiourea. Addition of 600 micromolar thiourea increased D over PD by 10% to give rise to the maximum value of D over PD equal 0.94. To summarize effect of thiourea, when thiourea is added to electrolyte, it is chemisoft on palladium surface. So, hydrogen recombination step on palladium surface is poisoned by the chemisoft thiourea. Then, desorption of hydrogen from palladium is inhibited. Maximum D over PD is 0.94. attained. Therefore, the urea is effective to have the over PD higher than 0.9. Next, I'd like to talk about deuterium loading in palladium with spattered gold film. Gold is electrochemically less active than palladium. So, when most of the palladium surface is covered by gold film, current density on the exposed palladium surface could be raised substantially, and this could lead to higher deuterium loading. Three types of palladium cathode with 7,000 ohms of gold film have been prepared by RF magnetron sputtering, controlling the surface coverage by gold film to 80%, 97%, 100%. This figure shows change of D over PD with time on palladium with spattered gold film in 1 molar LiOD at 10 degrees centigrade, and current density is 30 milliamperes per square centimeter. Loading rate of palladium with gold film becomes lower with increased coverage of the surface by gold film. The palladium cathode totally covered by gold film has loaded by deuterium as well. Therefore, it seems that deuterium atoms permeate through gold film and are absorbed into palladium. This figure shows dependence of D over PD on current density for palladium with spattered gold film in 1 molar LiOD at 10 degrees centigrade. The green circles are D over PD on palladium without gold coating. The triangles are that on palladium covered with gold film by 80%. The squares are that on palladium covered with gold film by 97%. Cathode loading is greatly improved by spattered gold film. The palladium cathode, 97% covered with gold film, gave maximum D over PD equal 0.94, while palladium cathode, 80% covered with gold film, gave 0.92. This figure shows dependence on overvoltage on current density for palladium with spattered gold film in 1 molar LiOD at 10 degrees centigrade. Overvoltage on gold cathode is a little bit higher than that on palladium, about 0.1 amperes per square centimeter. Overvoltage of the palladium cathode with gold film is significantly higher than that of gold. Next figure shows dependence of D over PD on overvoltage for palladium with and without spattered gold film in 1 molar LiOD at 10 degrees centigrade. The D over PD on palladium with spattered gold film becomes much higher than palladium without gold film. loading of palladium cathode with gold film. Deuterium atoms are soft on gold film, which were generated by polymer step of hydrogen electrode reaction, permeated through gold film and are absorbed into palladium. Then, high overvoltage is generated. Therefore, maximum D over PD of the palladium cathode covered with 97% gold film is 0.94. Next, I'd like to talk about cathode materials. First, D over N on palladium-rhodium alloys. This figure shows change of D over N with time on palladium-rhodium alloys in 1 molar LiOD at 10 degrees centigrade, and current density is 50 milliamperes per square centimeter. This is palladium, 5%, 10%, 15% rhodium alloy. The deuterium loading rate on palladium-rhodium alloys are greatly reduced with increasing rhodium content. Next figure shows dependence of D over N on overvoltage for palladium-rhodium alloys in 1 molar LiOD at 10 degrees centigrade. The green circles are D over PD on palladium. The black triangles are D over N on palladium 5% rhodium alloy. The open squares are Z on palladium 10 atomic percent rhodium alloy. The D over N on palladium-rhodium alloys increases with rhodium content. D over N equals 1.0 is achieved for palladium 10 atomic percent rhodium alloy cathode. This figure shows dependence of overvoltage on current density for palladium-rhodium alloy cathodes in 1 molar LiOD at 10 degrees C. Overvoltage on palladium-rhodium alloys are higher than on palladium by 0.2 volts to 0.8 volts. To summarize loading on palladium-rhodium alloys, deuterium loading ratio on palladium-rhodium alloys are higher than on palladium. Maximum D over N is 1.0 for palladium 10 atomic percent rhodium alloys. Therefore, there is a possibility that palladium-rhodium alloys can be used as cathodes in excess heat measurements for D over PD higher than 0.9 region. Next, I would like to talk about D over N on palladium silver alloy. This figure shows comparison of H or D loading on palladium and palladium silver alloy cathode at 10 degrees C. The green circles are D over PD on palladium. The black circles are H over PD on palladium. The open squares are D over N on palladium silver alloy. The black squares are H over N on palladium silver alloy. Hydrogen and deuterium loading of the palladium silver alloy cathode is much lower than palladium. Next figure shows dependence of overvoltage on current density for palladium and palladium silver alloy at 10 degrees C. Overvoltage of the palladium silver alloy is almost equal to that of palladium. This figure shows dependence of D over N and H over N on overvoltage for palladium and palladium silver alloy at 10 degrees C. The D over N as well as H over N on palladium silver alloy is much lower than palladium. To summarize loading of palladium silver alloy, the D over N as well as H over N on palladium silver alloy is lower than on palladium. Therefore, palladium silver alloy is not adequate to attaining higher D over PD than 0.9. Next, I would like to talk about H over PD on palladium silver composites. The composite of palladium and silver made by diffusion joint of those plates. Using the spark plasma sintering method was studied and its loading characteristic was compared with palladium and palladium silver alloy. This figure shows dependence of H over PD or H over N on overvoltage for palladium, palladium silver alloy, and palladium silver composite cathode in 2.8 molar sulfuric acid. The green circles are H over PD on palladium. The black triangles are H over PD on palladium silver composite. The open squares are H over N on palladium silver alloy. The H over PD of palladium silver composite is much higher than palladium silver alloy, probably due to higher cathode overvoltage. This figure shows dependence of overvoltage on current density for palladium, palladium silver alloy, and palladium silver composite cathode in 2.8 molar sulfuric acid. Overvoltage of the palladium silver composite cathode is much higher than palladium and palladium silver alloy cathodes. This figure shows change of H over PD with time on palladium and palladium silver composite cathode in 2.8 molar sulfuric acid, and current density is 20 milliamperes per square centimeter. This is palladium. This is palladium silver composite. Loading rate of palladium silver composite is much lower than that of palladium. Therefore, the mechanism of loading of the palladium silver composite cathode is different from palladium. To summarize, loading loading of palladium silver composite cathode. Overvoltage and H/PD for the palladium silver composite cathode is much higher than palladium and palladium silver alloy cathode. Then, loading rate of palladium silver composite is much slower than that of palladium. Therefore, this result shows that the mechanism of loading process is different on palladium silver composite cathode. Conclusion 1. Modifying the palladium surface by chemical process as well as by thin metallic film, which is electrochemically less active than palladium, is an effective way to achieve D/PD higher than 0.9. 2. Palladium rhodium alloy cathode give D/M equal 1.0. Thank you.
I'm sure we'll have a number of questions. Professor Kunimatsu will also be interacting on answering some of them, so please come up to the front and answer questions.
I want to congratulate you on a very fine presentation and very fine work. And as an industrial chemist, I'm pleased to see that it's not all physics. I'd like to ask a number of I'd like to first remark, I had expected when I came to the meeting, because of the problem of the sporadic nature, which we are severely criticized, I was somewhat disappointed in not seeing more investigations of this type. First, may I ask you, do you use tetramethylammonium hydroxide? Although the salts are quite stable, did you notice an instability and a breakdown of your base when you went through the experiment?
KG.
I'll take the question. We checked the electrooxidation possibility of tetramethylammonium hydroxide by conducting cyclic rotametry up to 1.5 volts. But we saw no electrooxidation of this compound. So it's very stable electrochemically at negative side as well as positive potential side.
Thank you.
I'd like to follow that up.
Let me finish. Should you, and this is obvious from what your curve showed, should you be working with ice water in your experiments, since your temperature coefficient shows that you get higher DO/PD ratios at lower temperatures? Why not work at a low temperature?
Yes, we did actually down to minus 30 degrees C. But the problem is, you are right, we can increase loading ratio at a lower temperature, but loading rates become very slow, so it makes it almost impractical to work at low temperature. You can understand, it takes many hours and days, and then we need quick loading. So
I understand.
maybe we could try.
Also, your thiourea opens up a whole area. There are a great number of thiols and thionium compounds that you might use. And finally, and I'm sure it's obvious to you, and you may have thought it, the time doesn't permit it, it's always easier to suggest experiments than to do them. Did you take your rhodium alloy, say 10%, and also work with thiourea so that you would block the surface?
Yes, we have done that experiment. We add Taiwan to 5% loading per hours. It gave us a very strange behavior for the first time, but after some time, the Taiwan gave us a very nice effect to achieve a load ratio of 1 all the time. So there is very strong hysteresis during the experimental period. So I think the consumption of Taiwan on this alloy changes when we apply overvoltage, and we do not understand fully this process yet.
Let me just end by saying I compliment this bit of research, and I think it was well presented.
I quite agree.
Thank you.
KG, have you been able to characterize the calorimetry of a tetramethyl ammonium hydroxide system?
No, yet, because we have to synthesize deuterated tetramethyl ammonium hydroxide, which we are now doing it. So maybe we can report the result sometime in the near future.
I'm sure we'll all be anxious to see them. Tom?
When you, a practical question, when you coat these electrodes with gold, do you coat the ends as well? And also, do you see any change or tendency of the gold film to peel off during the process?
Yes, in our early experiment, we saw the peeling off, but we are now doing some additive treatment after we deposit gold film. Then we have less chance to have the peeling off problem. But all the data she showed are still taken by the active cells. So we'll see if the electrode, we'll see the peeling off is really taking off when we finally open our experimental systems.
Thank you.
Let's thank the speaker again. Our final paper this morning is a contribution from ISCMNS and will be presented by Dr. Shivani. He informs me that the schedule has dropped to his co-authors, so he will rectify that right now.
Okay, this work was made with a joint collaboration with physicists and electrochemistry. Stein wanted to thank some people that helped with very deep discussion and suggestion about our work, mainly Ferrarotto, Preparata, Visce, Ennio, and Kulimatsu. The place comes from the Tanaka company between a joint program and IMRA materials too. The outline of our work is to try to find a correlation between metallurgical properties of palladium. This way we developed new kinds of plate with hardness as large as 300 meters, current density. So we developed a new procedure to give very high peak current, higher than 1 ampere per centimeter, over voltage larger than 1 volt was usually reported, and to temperature loading we can reach in a repeatable way 1-to-1, and in an experiment now in progress with some IMRA materials we get 1.2-to-1. So this is a way, a status record about 1 year of experiments with very high power pulse. We started up to 30 kilowatt for microsecond of pulse. Moreover, I would like to anticipate that we found some HF neutron in a systematic way during loading and reloading of the palladium plate. This happens only when there are some typical condition of loading ratio. So we think that neutron effects comes mainly because particle emission phenomena. So, as generally reported, to get HSE is necessary to overcome the limited value of level vibration larger than 0.84. So we found the relation between the level ratio, current density, or voltage. We will think about this. So the way is a simple way to increase current density, but there are de facto some saturation effects. Up to now, the methods used to get HSE, to get large value of loading ratio is used cold water procedure. So it's possible to increase the hardness from 50 to 170. But as drawbacks, there is the possibility to get embarkment of palladium and then after cracking of the material. If the material is cracking, it's not possible to get HSE. Even the apparent loading ratio is high as 0.7. 0.87. Is the usual relationship between hardness and loading and the cold loading percent process. The drawback of cold loading process that the repeatability this project is not as high as people wish. So this is a batch of experiments with the same cold water procedure, but different batch production. The higher value, the red lines, comes from the same batch produced Takahashi at the beginning of the experiment, and you get the results. This is the effect of annealing palladium. The hardness decreased from 1 to 60 up to about 60 meters. So, following this idea, we developed the joint experiment new kind of palladium plate with additional standard copper compounds, and then we get hardness as high as 300 meters. After that, we annealed these materials for 2 hours at 100 Celsius. This check is important because if the experiment of Richard hazard, so they declare, so the temperature of the palladium is about 100 Celsius. So it's necessary to check what happened at this temperature. The result of the experiment is practically no decreasing of hardness at this high temperature. This is another cross-check about density at the same temperature changing. So practically no effect. Means good. This is a similar check we made at 700 Celsius, like the conventional palladium material. And so in this way, the hardness decreased from 300 to about 130, but still a high value. With the conventional plate, so 260. The other way to increase the loading is just using the tougher regular solution. Means it is of over voltage, and this the value is proportional to the logarithm of current density. Moreover, as you get from Enio and we started doing, about tougher is necessary to take into account only the two components when we switch off the current. This figure is the fifth tougher component, just due to current density. It's called the eta 1. For eta 2 components, it's due to the level of absorption. It is over time, and not only the level of absorption, but even in water or lithium or several things. So the only good component, beautiful, from the point of view of the technology, is eta 2 fixed. When we switch off the current and leave the palladium in open chip condition, this is a relationship of eta 1 component means the tougher component increases the current density. The latter are reported data only up to 1 ampere per square centimeter. We reach about 7 ampere. So, the instrumental limit of about 0.6 ampere per square centimeter comes from two concomitant effects. One producing increasing of the electron liberation, the other one decrease. So it's necessary to optimize to avoid decreasing, to avoid the recombination of the deuterium with the surface of palladium. Moreover, electrolysis increases the hardness from time, so there is compromise between the table. Another way to increase hardness is to follow the so-called Takashi procedure, means seeking current between low and high current density. This way it is possible to get some increasing of hardness. Graphs show the value of hardness of palladium before electrolysis, through line, and after electrolysis. So this is about 20% increasing of hardness, but the data are, the spread of data are very large. So to make a local resume, the main condition which is to get an HC is to reach a value of loading ratio larger than 0.4, 0.0, without taking of material. Moreover, the value palladium ratio increases current density. So there is like an ideal condition. Current density is large as possible, recombination as low as possible. So we decide don't have poisoning of the surface because according to us, after it will be difficult to correlate the overvoltage values and the true deuterium. A possible solution to this problem is to give pulse current at a very high peak value, more larger than 600 ampere per square centimeter, for very short time duration, of orders of microseconds or less, at enough low recognition rate from 2 kHz in the microsecond region, or up to 20 kHz if the pulse shape is enough short. In some way, we have to maximize the level of absorption because it is proportional to the logarithm of peak current and to minimize the level surface recombination because it's proportional just to the mean current value. another extra benefit, there is some possibility to loading even the tetrahedral sites that are endothermic, just because we give a lot of peak power to the palladium plate. Just want to remind you that the theoretical limit value of the loading in palladium is 1 to 3, about 0.93 in the tetrahedral site and 2 in the tetrahedral site. The apparatus that we used is the same we used last year, so it's very well tested. And we just change the area where is the current generator. The new approach is the following. We made a very powerful pulse trigger, and we get peak pulse. So we acquire for the mean current, mean voltage, and we make it online by fast multiplier, multiply between peak current and peak voltage for the power difference. Moreover, we measure the overvoltage. All the system is completely controlled. Works, this is our approach. Here is written our pulse. This is the power pulse. I like to stress all the system works just because there are two regions. One region the low impedance regime when we give the power pulse, and another region, the large time, where the system is in an open condition system. So, regime. So we can read the overvoltage. This is the set for overvoltage in the instruments. This value, this is the power calculation. So after power pulse, we wait 30 microseconds to avoid oscillations and so on, and after we use the overvoltage. This is done continuously with the experiment. So it is a true overvoltage experiment, because in all the conditions, one blank made with gold. We spend more than 30% of our time to make blank of the system. And this chase, we check the effect of apparent loading in gold plate, just because identity experiment will tell you is dissolved in the heavy water in all the cell. Our cell is quite big, about 1 liter volume, and that's liter of heavy water. So the error that can be is 0.01. But after we subtract 0.0, this value by diagnosis. This experiment, the peak current is about 160 ampere. Because the plate is about 12 space centimeter, is peak current density about 1.3 ampere per centimeter. This experiment is made with very hard. This is the second experiment that we make by studying the same parameters of gold plate. So it's easier to understand. Others are the biggest, density 11.89. Total impurity was about 3,000 per liter, quite a lot. The green line is the theoretical quantity deficiency of the loading. according to Fabi rule. So we look at 5 kHz, the pulse pressure nominally spaghetti in nanosecond, the mean really about 700, because there is time for fall time, last time and fall time. Peak current is 1.3 amperes. The mean current is as low as 5.3 milliampere. So we call quality ratio between peak current and mean current is as high as 150. The peak voltage in the experiment reached on 30 volts. So after about 5 days, we reach a loading ratio as high as 1:1. This figure shows the absorption rate, so it means how fast the data is absorbed versus time. So comparing this graph with the previous, supposedly we identify the called alpha phase, beta phase, super beta, gamma, and so on. Orange is the this beta phase, the green, orange alpha phase, green beta phase, blue between beta and super beta, and gamma phase of each up to 1. This is the relationship between time and the voltage that we get. This value has to be subtracted for the TAFE components is about 4.665. So we reach about 1 volt for voltage. This is the relationship between the lumbar loading and the over voltage. This experiment is made with a very fast pulse. We don't know what is the optimal loading, preloading condition. So we try one condition that is easy to do some way. So we make the pulse total time of about 2 microseconds in time. And the mean current is 4 milliampere, same of before. After that, we look what happened. And it seems that after 2 days, more or less, the palladium reached some stable value of 0.65, the conventional beta phase. So we try something to increase the palladium ratio. So we increase the peak current and we reduce the frequency. After that we wait again and we saw another stable phase. We increase peak current and increase frequency and so on. Exchange we reach about 0.95. We repeated this experiment around for 3 months. We repeated this experiment several times. And after we found the optimal, according to us, loading procedure. And this plate gives very large HSC several times, and it depends on the story of before loading, so it's quite complicated. This figure is showing the speed of absorption in the previous, and you can see how hard it was to reach the value of 0.95 without optimizing the current. The conventional figure which will be delivered looking at the over voltage. Obviously, as it will correct from eta 1 TAFE component of the various peak current. So it's all standard correction. This is one of our typical results. Displayed. Green line, blue line is the blend with the gold plate in this almost the same condition, frequency, pulse duration, so on, and red the palladium plate. We found there is some optimal region where the HFIT has the maximum value. This change at 15 kHz transmission and with a peak current density of 5 ampere per square centimeter. The peak voltage is total of 100 volts. This day, we would like to check some old plates we had last year from IMRA materials that we studied last year with conventional cellular regime. And this is a linear data because experiment is underrun, it's running now. We give the optimal current procedure to increase loading, decrease loading. In this case, we get a loading ratio as high as 1.2. Is almost full palladium plate. The hardness is the higher value is possible to reach without poisoning of palladium cells. So it's about 1.2 years. For comparison, this is the results that we get last year, the blue line using the Tagashi procedure of Salvador. Last year we get the loading ratio of about 0.75 in a very short time, but after saturated. With this plate last year we didn't get HFIT. Only for a short time, some hours, after loading and deloading. I mean was really 2%, not enough. So comparing the results with very big power pulse and Saradut, we can see that the efficiency of loading is remarkable low with the fast pulse, but reach higher value. Similar graph for the speed displayed at the sort the very faster than the other of before. So the very hard plate is a little bit slower to load the value, and after reach the value of 1 to 1. This one is faster at the beginning, it's a rate at 1.1. We see what will be done in this plate. So this is about over voltage, and seems that there is some cracking when reach 0.9. But we don't are very sure if it is cracking of material or just sign of phase transition from octahedral to the radial side, because it's very close to the value from the theory of 0.92. So we are waiting what happens. You need to do about loading and over voltage time or strange phase transition. This experiment will obviously measure HSC decay. The input power is an order of 1 watt. So since there is HSC even at the beginning of experiments, it's not the crystality of these results. So we interpret strange results just because there is gradient concentration, the surface, and the back. So over time, they increase and increase HSC, which is because the back increase. This is showing the input power evidence and output power. Moreover, we make some way strange study because we want to analyze what is the effect of lithium coating of lithium on the plate. So we started deeply the effects of lithium on gold plate that did not solve the inductive palladium. So this effect of coating the lithium in palladium in gold plate. So this experiment is quite fast on time. We give current for about 5 minutes after switch off and measure the overvoltage after 3 minutes to minimize possible overvoltage. This is one possible question that suggested from me. So this effect is due to lithium. At the low frequency and the low peak current, we can see that the effect of cleaning the surface due to the deuterium coming down from the palladium avoid deuterium loading cells. Means the green line is higher than the red line at low peak current. The increase in the peak current effect. At 5 kilohertz is almost flat because we decided to make the preloading at this frequency and this value in time. In the most range in if it was up at a very high frequency. So we have something similar to very low frequency. This is possible in some way to clean the surface of palladium if there was too much lithium to surface itself. I'd like to summarize. It was these things. It was with Spindle demonstrated it was possible to perform electrolysis even in the megahertz region. This is a multi-step effort, so I think it's a very long explanation, so it's not sense. supposed to get in a reproducible way high-fidelity of the order of 1 to 1, or a bit more in a new experiment, just to give you enough high peak current at full intensity and proper frequency and pulse duration. According to our experiments, the mid current density play a minor role with respect to the peak power value. And okay, it's necessary that the peak frequency, peak power pulse is enough high frequency to avoid the loading during pulse. And the limiting frequency depends upon lithium coating, poisoning, and so on. Moreover, the compatible analysis of EDA2 components show that it's possible. So there are several regions. One region where it's possible to maximize the deuterium absorption, minimizing lithium deposition. One region where the effects are similar, and another only lithium. Moreover, the lithium coating increase, just increasing the pulse duration. So it's optimistic. We have developed a protocol how to get chassis. First, we have to load the deuterium up to some critical value without using lithium or minimizing lithium, means to 0.85. After increase the lithium coating, because according to us is anti-cracking agent. Later, increase peak current during get HS increasing HSs. Obviously, the limiting value of peak current and the voltage depends on the metallurgical property of the palladium and the ceramic. As a bonus, we found there is some proper frequency where it's possible to clean the surface of palladium if too much lithium coated it or lithium. Thank you.
Carol, we go to a microphone.
Okay. The HHS range from 10 up to sometimes 25%, but very complicated story depends upon the previous loading, surface conditions of the other stuff. It's really complicated, but really effective.
I wonder if you could explain to me just how you measured the loading in this experiment. I guess I didn't understand.
Okay, we measure the loading ratio just by volume. So we compute by Faraday the gas that has to be developed because of electrolysis, and we check what we really measure. Every measurement uses as blank gold plate. So if some systematic errors can be are removed just because blank with gold.
Any questions? Tom Passel would like the last word, and I'll let him have that, and then we'll thank Dr. Chilani.
Just remind you right after 110, we'll have a special on Kim, 1934 discovery of fusion. And after that, at 1:30, panel discussion will occur. And most of the people that you see here will speak to us for the order of 40 minutes, and then we'll have a chance to question them and make a question themselves. So the time will quit as late as 3 p.m., but if you run out of gas, we'll quit a little bit earlier than that. Thank you.
Let's thank all of the smart speakers.
How you doing, Tom?
I'm in that. That's nothing. You'll get that recorded by the media and exaggerated. That's no problem. Those Westinghouse, the French did the right thing. They worked with the Westinghouse design. They said, we'll take it, flaws and all, and then we'll improve on it. And by damn, the French plants over there are excellent. They're working 80% capacity factor. You've got a complete nuclear fuel cycle. The French are making money hand over foot, and the French came up and with the cooperation with Constellation, came up with the first coal fusion reactor and ended up dominating the world. All I would say is, vive la France!
Yes, but even so, I know that.
Oh no.
I know of the belief that countries compete, and that it's companies that compete.
Yeah.
It's irrelevant now whether it's France or Japan or
Right.
wherever. The important thing is that it's done.
Yes, what?
Mankind. This fact saying,
Or it's in Beijing.
yeah.
Hi.
Hi, Mitch. What do you think of this wonderful conference?
Gene, I didn't plan to be near camera.
Oh, quick.
That's true.
Might be. Well, I'm gonna go check them right now. Gene, come and point your camera.
Come over here. But the thing is, you gotta. Oh yeah, you got the little greens and lights. Just the day I'll take a picture.
Up the waiters.
No, the other four speakers.
These errors, what he thinks is a back-to-back track. There are another one like this. I don't know why he put the error here, but anyway, there are at least three pictures that he thinks it's a back-to-back. Martin just told me, which I didn't know, he published another paper about a year later, and there are several pictures of this car shown in there. I haven't seen that yet. But let's do some kinematic first and see what kind of angle is involved. You come in with 60 kV lab energy and hit the target. Target was ammonium sulfate, new direction. And then, of course, one channel is this channel. This is the channel is trying to observe. And if you do the standard kinematic, you can calculate that looks like this. You have at the high energy, it's only 160 degrees, low energy nearly 180 degrees. And of course, if it's a 1 or 2 kV, you could have a 2 degree deviation, which may be within negative. Now, once you identify a nuclear process as a fusion, because you can calculate the fusion probability. This is the standard formula. And since you are doing beam experiment, you have to know energy loss during the collision. And those can be obtained from Anderson's book. So these are known quantity, which is very accurate. So by putting those in, you can get probability can be written in this form. Unfortunately, the index given for this energy range can be written in exponential form, so that you can actually dynamic for integration and end up with the basic formula. Okay, and knowing the gamma energy, you can calculate the probability of the interaction as a function of energy, as well as fusion rate if you know the incoming flux. And they were using like 100 microamp current. I was amazed to find out that in 1934, they were doing more like a standard nuclear physics experiment we do nowadays. I guess that was a period to British science most active here. Anyway, result is this. You have probability fusion as a function of incoming energy in the lab energy. And then I normalize this to 1 and then see compare with the other. Now, if it's a 2 degree event corresponding to 2 kV or 1 kV, you got the trillion factor dextrine to observe it. If in terms of rate, this is calculation is most improbable for D to observe 2 kV band. If you believe conventional demo scaling technique. Now there are many artifacts one has borrowed, and because I challenge you to think of what artifact you think of, and let me know. I thought of several things, and throughout, this was objection by Mario Ravino, my colleague, and so I worked out the formula. What if incoming 160 kV hits a target, and then scatter from a target, and then produce a proton deuterium back to back? And of course, this back-to-back event can occur at any energy because of kinematic. So I have to estimate what is the probability of first scattering beyond the 30 degrees because of the geometry I will show you later. Now, if I compare with the forward scattering amplitude with the 30 degree scattering amplitude, this ratio is almost 10 to the minus 8. So it's most unlikely that this event, this kind of event, is mimicking that back-to-back. The reason why I choose 30 degree or so is that if it occurs, it has to occur beyond 30 degree to really see the track. If it's less than 30 degree, of course, you hit the wall and it won't clean the track as you have seen. So my conclusion for this part of talk is that back-to-back DT track occasionally observed by me in 1934 appears to be anomalous. That is, it cannot happen with a conventional estimate based on gamma effect. Of course, the other possibility is the artifact, which I haven't thought of everything. Maybe you can think of any artifact and let me know. Now, since this experiment is very inexpensive, and maybe with a modern facility, or maybe modern counting methods, maybe one or two repeat this experiment, see whether his data is incorrect or not. Let's assume that his data is correct. Seeing a real event, not artifact, then the question arises, the gamma effect may be not correct. Now, there are some evidence from other light nuclear reactions that gamma effect becomes larger at the low energy. This is a few examples I'm showing. This is conventional gamma effect extrapolation, and it deviates, and those dotted curve is assuming that there is an electron screening energy of about 200 to 300 electrons. But the conventional theory for the electron screening cannot have that large number. It's much less than 200. In fact, it's less than 100 electrons, so that the conventional electron screening will bring something like this. So this is a big problem for the theoretician to understand. There are some other data. Okay, now let me spend the next maybe 5 or 10 minutes or something. 7 minutes. Okay. I'll go through my image formulation of scattering theory. I'm going to just show how this is done. You sketch the wave function as incoming wave and stereo divergence scalar wave, and this tells you amplitude. And you make a partial wave expansion, and quantity written as eta is called the S matrix. So if you determine S matrix in some way, theoretically, then you can get elastic cross-section using this formula and reaction cross-section using this formula. Fusion reaction cross-section will be calculated by 1 minus S matrix squared. And in partial wave, we can define partial wave cross-section in terms of those S matrices. Now, given potential model, you assume you can compute what S matrix is. And when you do this, well, normally you can get a solution for external wave function in terms of incoming wave and outgoing wave, and S matrix essentially sits right here. That's the wave function solution which is making outside this nuclear surface. Within the nuclear surface, you really don't know exactly what to use, but later I'm going to parameterize that in most general form, you don't have to really bring explicit form of the interior wave function. And I will get to this result, and I will just show you one figure of how this is obtained. What you do is you define P matrix, and this happens to be inverse of R matrix. It's a logarithm derivative, and in a continuous state, it's usually complex, so that you have to have a real part and a imaginary part. So I'm going to parameterize the two numbers, two real numbers. The external wave function has this form as I told you before, S matrix here, incoming wave, which is normalized to unit flux, and then outgoing wave. And again, you can define the P matrix as a logarithm derivative. And if you do the calculation, you can calculate the eta, S matrix, in terms of all these quantities I introduced. And the external wave function, if you use whatever wave function you wish to use, like Coulomb wave function outside, any diagonal type potential can be solved and has to be this form. This is a Lagrange solution. And once I know that, I can take the derivative, logarithm derivative of outgoing solution at the nuclear surface, and again, that is a real imaginary part, and the real part of there is a imaginary part that we call S. Okay? So that's the result. That's what I obtained. Notice that I have not assumed what the internal wave function is. That's a many-body program, and I can introduce model, but without introducing model, I ended up with this more general formula. Later, when I put this model for integral, I can put those K1, K2 expressions. But look at this formula. If it turns out that these two cancel exactly, and if this is equal to that, the transmission coefficient, actually I should say reaction coefficient, goes to negative 1. Instead, if I choose this to be 0, I can get the gamma approaching. But this is more general than the gamma. And for particular conditions which allow me to make a translation, I can make both 1. And let me remind you, this formula is most general. That is, it applies to any parallel particle interacting through the impulsive potential. Like a two-charge particle, it doesn't matter DB or PB or deuterium, palladium, whatever. As long as nature is kind enough to cancel it, then you have a transparency. And of course that we don't know. Experiment has to tell me whether there is a transparency. That's for you to find out. And I did some simple analytical calculation and you get the response. Any potential. Okay, now I think my student applied to conventional data. This is the reaction you guys are all worried about, ED. And this is up to MeV or 10 MeV or so. And with the two parameters, I can fit the entire range of the potential. And this is just S. Now, there is no reason to exclude every one or two higher resonances. If there is a transparency at the threshold, you can add to this so that you don't violate conventional gamma type imaging. How bad is the gamma factor? You are only trying to check this region is a gamma factor. And of course, question is, can the other formulation scale same as gamma factor? My time is running out, so I'm going to give you a very provocative, as Martin said. Before we walked out this morning, I firmly believe that gamma factor must not violate. That is, John Heidegger's first miracle could not happen. But gamma factor is one approximation to many possible solutions of quantum scaling theory. And God knows what the parameters are. As an individual, I feel very humble now. I should really say gamma factor is original. That's one provocative statement. And hence, any objection based upon gamma factor are open to question. They may be premature. So I think we need to be more open-minded on what the result of our vision, as long as that experiment is reliable. And of course, ultimately, reproducible experiment will result with right. And if this scheme is correctly expression with some of the observations you guys are making, then there need not be just DD. You can have TD or some impurity in the system, as long as nature is kind enough to pick a particular parameterization value, which cancels those two terms I talked about. And remember, that formulation is most general formula I've written. I didn't assume any particular potential. And if that's the case, then
the branch ratio may not be due to DD. Maybe we are beating the wrong 4 or barging at the wrong 3, if that happens to be the case. But I think ultimately we have to really look for nuclear edge. And once you find the nuclear edge, then you have to think hard whether that corresponds to a particular scenario. There are so many scenarios I think of. That's my point.
Thank you, Jan. One good question, yes. One good question.
Professor T was my professor. He was a very fine man. He became one of Rutherford's favorite scientists. He almost discovered the neutron. And unfortunately he's dead now and he's gone up to heaven. If by any chance you get called to go by heaven, I would advise you not to tell me he discovered cold fusion. If you want to do this experiment again, at that time the beam intensity was very small, therefore use a thick target. So if you're going to do the experiment again, try and get in the thickness of the target and find out what you get.
Okay. If you want to answer, use the microphone, please.
Your objection. That is, if you have a thick target, then there's the rays, it might cover an entire range of the energy, so that if you made a measurement that, let's say, down to 10 kV, you're essentially measuring down to zero energy. That's what you're saying. But that thing I hold, I haven't shown this, but as you make this cancellation occur at the lower end, that is go to threshold, the energy dependence becomes very narrow. And when you do DX and target, like the metal target, compared to what the beam, the energy loses so quickly that energy streaming through that narrow window doesn't give enough factor compared to low Z target, which makes. So there are lots of open questions. But to say that all of the experiment, because it's thrown now, maybe essentially is not correct. There are lots of factors within.
Thank you very much. I'm going to call it quits now and ask my panelists to please come forward. Thank you very much. Panelists, please come forward. And before they do, I have an announcement from the organizing committee by Mike McCoury for giving him 2 minutes to tell you where the next meetings might be. I'm sure you're waiting for us to draw the envelope out of the hat and find out which city wins this one.
First of all, we've come to the end of the formal presentations, and I'd like to thank each and every one of you for your participation and presentation in this conference. I thought I was going to have to do a lot of work this week and running around, and indeed that turned out to be true, but I think it also turned out to be very well worthwhile, and I thank you all. The Global Organizing Committee and the International Advisory Committee met last night to decide where the future next 2 conferences will be held. With much persuasion, Stan Barnes and Martin Fleischmann have agreed to organize and assist in the organization of the next conference, ICCF-4, which will be held probably in March or April of 1995 on the normal 14 or 15-month schedule of these conferences, probably in the south of France, probably somewhere as unpleasant as Nice. In the spirit of the Olympics, we have decided to organize not the next one, but the next 2 conferences. As you will all recall, the schedule for these conferences has moved its location in the order North America, which is where Hawaii is, Europe, Asia. The next one in Europe will be in France. The following one in Asia will most probably be in China, and Professor Xinjiang Li has agreed to look into organizing that conference in China. Thank you all.
Thank you, Mike. And I should have acknowledged Mike's very hard work in
Push that down.
Your 10-minute quick history
Just
by
look at that. Thank you.
Ed Storms, and each one will have 3 minutes to give us their view of the most significant thing that occurred at this conference. They're in alphabetical order following Ed Storms, except for Daniel Gossi, who has to make a claim a little bit early, so he's a little bit out of order. But he'll forgive me for violating that alphabetical rule. All right, Ed?
I'd like to give you a personal and very unscientific view of the cold fusion field from a path less traveled. I don't think we qualify as a road just yet. I'd like to suggest that there are 5 stages. We're presently in stage 3, so I won't have to get in and try to tell you the future. Stage 1 started when Dr. Pons and Fleischmann partially jumped and partially pushed into the Coliseum of public awareness, and the lions were very hungry. Fortunately for Steve Jones, he wasn't very tasty to the skeptics. But this event caused a tremendous change in science in many laboratories. A lot of people who were gifted with an imagination and had access to suitable equipment started to try to find ways of reproducing this extraordinary claim. A tremendous amount of noise was generated, and out of this noise rose a few positive results. These were examined in great detail and were rejected. And a few very negative results were found in a number of well-known laboratories. These were given very little analysis and accepted. And thus we have laid the foundation of the double standard that seems to exist in the field even until today. The end of this period occurred when the URAB panel issued its report. This, from my point of view, was an incomplete report and very damaging to the field. Following that, the field went underground and became somewhat defensive. There were, gradually from the debris, arose islands of stability, EPRI in the United States being the principal one, but other islands in Japan, India, Italy, and later to be found in Russia. And from this information, an increasing understanding of the field developed. During this time, the argument for the skeptics was presented very nicely by Frank Close. Douglas Morrison took this view into the lion's den and did a good job of making the case to the cold fusion community. Eugene Malov popularized the case for the positive viewpoint, and a number of scientific reviews were written. Thus, the battle was joined. And I might point out that during this time, the skeptics provided a very worthwhile contribution to the field. They kept people honest, they forced people to examine areas in much greater detail than they would otherwise have done, and that contribution was exceedingly valuable. Well, gradually, the transition occurred into the phase we're presently in, and that is the transition to seeing the structure in its generality, to examining the bricks. And we are beginning to examine the bricks. We have discovered that the mansion that Pons and Fleischmann stumbled upon is far more grandiose and far more difficult to understand than was originally thought. At least 6 different independent methods of initiating effect have been discovered, and also there's growing evidence for a variety of nuclear reactions. This is, even within the cold fusion community, But unfortunately, during this time, the role of skeptics has died away because they have not kept up with the new results. And they have shown a growing evidence for a certain amount of pathological skepticism. This is not to say that skepticism is not warranted, nor that we are all doing a perfect job, but we do need a more perfect focused critique of what we're doing and what we're being delivered. I would point out, though, that I would perhaps thank the skeptics for what they're doing right now, because it is giving us breathing space between this and the next stage that I'll talk about. And that is that by keeping a vacuum in the intellectual community outside of cold fusion, they are giving us who are underfunded or otherwise not able to work at high levels in any field, an opportunity to position ourselves intellectually and financially in a field that will be at some future date exceedingly important. So they are actually our friends, if looked at that way. And in that context, I would suggest that we create an award. I would call it the Flying Pig Award. And it would be given to the skeptic who most successfully keeps the outer world in the dark about cold fusion. And you might have your own suggestions. Well, the next stage that I see coming, and we're coming close enough to that we can begin to feel the hot breath of success. It may not seem that way to some of you, but reality always wins out, and the reality has become overwhelmingly real. And at some point, major corporations as well as governments are going to realize that they have missed phenomena of unprecedented potential and importance, both from the financial as well as the national security point of view. And this realization will cause them to look around to try to find people who are competent to do work in the field. And they will look around and they will see only a few people. And we will suddenly discover we're abortion money and are quite popular. So I would suggest that you hang in there. The next step that we'll see, the next stage is somewhat in a more distant future, and that is that when you'll be able to find a small device based upon the cold fusion principle on the shelves at Walmart. And I would suggest that if you have patience and realize that the wheel keeps turning, and sooner or later we will rise up out of the mud and be at the top of the wheel, you'll feel a lot better about what you're doing. Thank you.
Daniel, 3 minutes, Danielle. Are you ready? You want to come up here or sit there and carry on? First point I would like to stress is that at this meeting, finally, people realize the role of the electric field in polarity. Contribution given at this meeting, as well as our experimental evidences, go into this direction. I remember that in past meetings, this field was completely neglected. Another point which was developed at this meeting is the indication, often at the level of hypothesis, of low-energy nuclear reactions. I believe this point source of risks for the credibility of our scientific community. If these statements and hypotheses will be not carefully tested in a very near future. The third point I would like to stress that I am not involved in theoretical physics, but what was presented at this meeting
seems to me without any particular novelty, and I believe the preparata theory still closest to my faith. And let me to conclude that in coming to this meeting, my expectations were to have a more experimental result, especially on EU4 and excess heat. More results of excess heat correlated to palladium metallurgy, as well as on loading ratio. My balance is that we have dedicated more time in discussing what has to be expected than what we found. I believe that the more useful discussions would be in discussing the experimental results. The efforts that are in progress in all the world to make application of a cold fusion seems to me one of the most evident results that we are not dealing with pathological science. Thank you very much.
You set a good example by using 2.5 minutes, and I appreciate that. Tom Claytor is next, to be followed by Martin Fleischman.
I'll keep this short. I'd like to thank the organizers for the choice of location, accommodations, the entertainment last night. It was very nice. I've noticed in the program that the nuclear section ranks just behind the theory in the number of submissions here. So I don't know what that means, but it's appropriate that there are many nuclear papers because I think that's what's going to give us the information as to what the real handle is. The heat is just sort of a one-dimensional item, but it's very important. It's the driving force, it's the funding force, if you will. But the nuclear measurements are the ones that we really have to address if we want to get a handle on the underlying situation. So, what do we have by these nuclear products? The neutrons, which are almost impossible to detect. The tritium, which seems to be a little more prevalent, lasts longer, it's easier to see. Some sporadic gamma results, charged particles, electrons, and isotope shifts, and the helium. The helium is there, and I think the most important thing I've seen, is the time-dependent helium evolution, and that's something that we've waited a long time for. It's been, the critics have jumped on that from day one, but it was a very difficult measurement to make, and it was worth waiting for. I think what we have to do now is look at all the material, see if there's any activation in the material, and continue the nuclear measurements on systems that have been very well characterized. Hopefully we'll become a little bit more reproducible as time goes on, and the nuclear people will be able to have assuredness that they will be able to get some sort of particle on. Thank you very much.
That's another record for only 2 minutes, Martin. You can have an extra minute, maybe, if you want. All right, come on up.
I'm sorry I'm late, but I got into a scientific discussion and didn't see the time slip by. Now, because I'm late, I'm also rather under misapprehension. I thought we were supposed to nominate the contribution to this conference, which impressed us most. Okay. Well, you have perfect control over me, even though you don't give me any money. Now, as being terribly interested in other people's science, I would of course be very tempted to nominate Jan Kucherov's work as the most interesting one, because he shows us, I think, that if this work can be successfully implemented, how we can get a great deal of information from a low voltage discharge system. And I must tell you here, use this opportunity to tell you that we have indeed reproduced some of Jan Kucherov's work ourselves in Sofia and Antipolis. Now, however, I'm not going to nominate Jan Kucherov because Jan Kucherov has recently been given the first award of the famous Truffle Prize. The Truffle Prize has been instituted by our Italian colleagues for the most interesting contribution in the field of cold fusion during the year, and it was awarded to Jan Kucherov. Jan got the Truffle Prize, and we ate the truffles for 2 days and nights, after which we couldn't eat anything for about 2 weeks. So, with great respect to Jan, I'm not nominating him here simply because he's so highly recognized. The paper I would nominate is that by Dennis Kravens. Is he here? He's gone swimming. What a sensible fellow. There are several reasons why I would nominate Dennis Kravens, which I made quite clear after his contribution. He had revealed to all and sundry many of our tricks, which we were trying to not proselytize about too much. So, of course, when somebody rediscovers what you have been doing all along, you feel drawn to it. But I think we have to compliment him. This is real science as it should be done in his garage, on a tight budget, on a very limited budget, producing an unbelievable amount of useful information. And the main reason, of course, why I want to nominate Dennis Kravens is because if you really want to get this thing to work, then do go and talk to him. He'll put you straight and he'll set you going along the correct road. So Dennis Kravens is my choice.
Dr. Guzowski, if I pronounce you right, are you here? No, you're supposed to be up here. We have to leap over all sorts of obstacles.
Excuse me for my English. Дальше тут говорить по-русски.
Dr. Guzowski is making excuses for his poor English, and the rest of his speech will be in Russian.
Я первый раз присутствую на такой прекрасной конференции.
For the first time he is present for such a wonderful conference.
Наиболее потрясающим был скачок из зимы в лето.
Most spectacular was the transition from winter to summer.
Но, к сожалению, мы так здесь плотно заседали, что полностью эти прелести мне не удалось ощутить.
But because of a very tight agenda of the conference, he missed most of the stuff.
Я занимаюсь ядерной физикой, и поэтому буду говорить об этой стороне.
As I'm a specialist on nuclear physics, I will talk about this.
По-видимому, еще долго после приезда домой я буду думать о тех материалах, которые я здесь услышал и увидел.
Even long after I came home from this conference, I will be thinking over the results I have here.
Но кое-что уже сейчас можно было бы высказать.
But some of the thoughts I can emphasize right now.
что основная критика в адрес холодного синтеза связана с отсутствием четких доказательств его ядерной природы.
As we can see, most of the critics are based on the clear and explicit proof of its nuclear origin.
Поэтому дальнейшие усилия должны быть все-таки направлены на то, чтобы провести то, что называется в ядерной физике полным опытом.
So, as I believe, the next efforts must be devoted to fulfill a so-called full experiment.
Полный эксперимент включает измерение всех участвующих частиц во входном канале и в выходных каналах.
As you know, the full experiment must include all the particles which take part in the input of the experiment and all the particles at the output of the experiment.
При этом надо проводить измерения энергетических и пространственных распределений продуктов реакции.
And either spatial or energetical distributions of the products must be made.
К сожалению, большинство экспериментов